In this video, we're going to introduce what is called the complex number field. You've probably seen complex numbers before, but chances are there are some little insights about them that maybe you haven't encountered before or could use a little bit of a reminder of, and that'll be useful to us later in this course. So just by way of introduction, suppose I give you the polynomial equation x squared plus 1 equals 0, and I ask you to solve for x. In the real numbers, we know this is impossible, because if x is a real number, then x squared is going to be greater than or equal to 0. So x squared plus 1 is greater than or equal to 1, so it can't be 0. Which means this equation has no solution. So at some point, somebody invented the idea of an imaginary number so that we could have a solution to this equation. So we define I to be a number with the property that I squared is equal to -1. And some people will write that I is equal to the square root of -1, which is okay as long as you remember that really that symbol means a square root of -1, because once you have one square root of -1, there is by necessity going to be another one. Because if I squared is equal to -1, then, well, what happens if we square -I? Well, then we get -1 times I squared, and that's -1 squared times I squared. And we already know I squared is -1, and -1 squared is 1. So that all works out to -1. So really there are two square roots of -1. There's I, and then there's also -I, its opposite. And that's the basis for the complex numbers. So we define the complex numbers to be those numbers of the form, complex number is a number of the form a plus bi, where a and b are real numbers. And when we do that, this is called standard form or Cartesian form. And when we write a complex number in Cartesian form, a plus bi, we have special names for these things, these coefficients. This is called the real part, and this number b here is called the imaginary part. Note that we use the term imaginary part to refer only to the coefficients. So for example, in 3 plus 5i, the real part is 3. The imaginary part is simply 5. It's not 5i. All right. One nice thing to know for later is that we can represent complex numbers visually using something called the complex plane. A complex plane is kind of like a Cartesian plane or an xy plane, except for the fact that when we plot a point in a complex plane, we are plotting one number, not a pair of numbers. So for example, 3 plus 5i would be represented in this way. I would mark off 3 units on the real axis, 5 units on the imaginary axis, and then at the place where those two lines meet, that would be the point 3 plus 5i. So that's how we locate a complex number in the complex plane. Another example, -1 minus I would be down here. 0, of course, would be right here at the center. 0 on the real axis, 0 on the imaginary axis. A pure imaginary number like -4i would be on the imaginary axis. And of course, we can also locate all of our real numbers in the complex plane. For example, the real number 6 would be out here, 6 or 6 plus 0i. So we can locate every complex number in standard form in the complex plane. Now, I mentioned this is called the complex number field. So the complex number field consists of all complex numbers of the form a plus bi, where a and b are real, and I claim this set, the set of all a plus bi, such that A and B are real numbers is a field. To prove that, we would first need to prove that this is a ring, and I'm not going to do all of the details here, but I do want to show a couple of examples of how we operate with complex numbers. So first, let's show it's a ring. So before I can start proving that the complex numbers have any kind of ring structure, ring field, or whatever, I need to define operations on complex numbers. So let's define addition by a1 plus b1i plus a2 plus b2i. So I'm going to show how to add any two complex numbers. We're going to define that to be a1 plus a2 plus b1 plus b2i. Okay, we're taking that as a definition for now. And we'll define multiplication as follows. If I have two complex numbers and I want to multiply them, then I do that in a way consistent with the distributive law. So I'm going to say that's a1 a2 plus a1 b2i plus b1 a2i plus b1 b2i squared. And then we're going to keep in mind here that we've defined I squared to be -1. So that comes out to a1 a2 minus b1 b2, because that I squared was -1, plus a1 b2 plus b1 a2 I. Okay, so now that we've shown we can add any two complex numbers in standard form and get a complex number in standard form, we can multiply any two complex numbers in standard form and get another complex number in standard form. Now at least we have operations. The next thing that we would need to do to show that this is a ring is we would need to show that these definitions satisfy all of the stuff we need for addition. So addition is associative, has identity, has inverses, also needs to be commutative. We require that for a ring. We would need to show that multiplication is associative. And because we prefer to work in rings that are commutative with unity, we would go ahead and show that this operation is also commutative, has an identity. We would need to prove a distributive law. And finally, if we want to show that C is a field, we would show every non-zero complex number has a multiplicative inverse. And I think that rather than regale you with the proofs of all these facts, that addition is associative, commutative, that multiplication is associative and commutative, I'll briefly mention that the identity for this ring is 0 plus 0i. You can verify that adding that according to our definition to any complex number gives the same complex number. The opposite of a plus bi is going to be -a plus -bi. And I'm just taking care there to write that in complex standard form. So rather than write -a minus bi, I'm showing this is the real part, this is the imaginary part. So those are additive inverses. You could probably prove on your own that the addition operation is associative and commutative, that multiplication is associative and commutative. Those are calculations. The identity, as you might guess, is 1 plus 0i, or as we often call it, just 1. You could check the distributive law, but showing that multiplicative inverses exist for every non-zero complex number, there's something to that that's kind of nice to show. So we'll do that together. All right, so to show every non-zero complex number has a multiplicative inverse. Here's what we're going to do. Suppose a plus bi is a complex number and is non-zero. Well, what does it mean for a complex number to be non-zero? It doesn't mean that A and B both have to be non-zero. It just means that at least one of those has to be non-zero. So A is not zero, or B is non-zero. Maybe both, but we don't know. And we want to find a multiplicative inverse. For A plus BI. Now to do this, I'm going to go outside of what I usually consider proper practice in ring theory, and I'm going to set this up as a fraction. So I'm going to say, what is 1 over A plus BI? So the reason I'm being a little bit cautious about this is because if I'm writing a proof strictly within the world of ring theory, I need to explain what this symbol means. And in fact, I probably need to justify that this symbol means anything at all, because to me, this would represent a multiplicative inverse of A plus BI, and I haven't yet established that exists. So what I'm doing right now is strictly scratch work. So I'm going to put in a little red box here, and we'll play with it inside of this red box. But we have played with complex numbers before, and we know how we can work with this. One thing that we can do is we can multiply this by something equivalent to 1. So we're going to multiply it by A minus BI over A minus BI. We do that because we know something from our high school education or maybe college algebra about these being conjugates, and the idea of multiplying by a conjugate being a useful strategy. So that gives us A minus BI over A plus BI, A minus BI. And now the merit of this strategy starts to become clear. Because when we multiply by that conjugate, we get a difference of squares. And so these two terms that we might otherwise get that involve imaginary terms go away. So I got minus b squared, that I squared is -1. So I have A minus BI over A squared plus B squared. And I know that's non-zero since A and B are real numbers, and A is non-zero or B is non-zero. The only way that whole thing could be 0 in the denominator would be if both A and B were 0. And they can't both be. We assumed our complex number was non-zero. Okay, now we're not yet at the point where we could introduce this into a proof because, again, I haven't introduced what this symbol means. But I can recast this as a complex number in standard form. So this here is a real constant. So what I'm going to do is I'm just going to imagine taking that real constant and separating that out into both terms. So I got A over A squared plus B squared, and then negative B over A squared plus B squared I. That's the same thing. And now this is something that is kosher to write in a proof about ring theory because this is a real number and this is a real number. And we've talked about what this means for real numbers. This means take this and multiply by the multiplicative inverse of this, which has been established to be non-zero. Okay, so end of red box. I think we're about ready to finish the proof. So here's how we would write this in the proof. We would say, claim that A over A squared plus B squared plus negative B over A squared plus B squared I is a multiplicative inverse, and in fact the multiplicative inverse of A plus BI. And then we would verify that. And that's something that we need to do in the proof because everything that we did in here really doesn't count. We did a lot of stuff here that isn't technically permitted in ring theory. So to verify this, we would just calculate A plus BI times A, let's give a little more room there, A over A squared plus B squared plus negative B over A squared plus B squared I. And well, what does that come out to? Let's just distribute this out. This is, so the first term is going to be A squared over A squared plus B squared. And then the outside term is going to be, sorry, even when I'm using this Druder property, I'm still mentally foiling things. I kind of tend to treat FOIL as though that's a taboo, like it's a taboo to say that. But that is always how I'm thinking when I do these. All right, so that's the outside term. Inside term is going to look like this. And then the last term is, let's see, that's minus B squared over A squared plus B squared I squared. And that I squared is -1. Now, one thing you may notice at this point is I'm just multiplying by using the distributive property. I'm not multiplying using the definition that I took care to write down earlier, this one right here. If I'm being really proper about this, I probably should be using this, because that's what I'm considering to be my definition of multiplication. The reason I'm not doing that is that I came up with that by using the distributive property for binomials. And so everything that I do here, if I'm using the distributive property for binomials, it's going to be consistent with that definition. And honestly, I can never remember that formula as easily as I can remember the distributive property. So that's why I'm doing this way. But really, we should be sure to honor whatever definition we're using for operations in our ring or field. Okay, anyway, so it looks like these two terms go away. And these two terms, I think something nice is about to happen there. That's a squared over a squared plus b squared. That I squared is -1, so I've got plus b squared over a squared plus b squared. So that comes out to a squared plus b squared over a squared plus b squared, and that is indeed 1. And I have no imaginary term, so this is 1 plus 0i. I've done that probably 100 times, but it's always rewarding to see that work out. So what does this mean? This means that every complex number that is non-zero has its own multiplicative inverse, which makes this a field, provided, of course, that we've shown the multiplication is commutative and that this satisfies all of the other axioms of a ring.